Alright, my dear children of class 11 science, we move to next topic. After the topic you learned in details, the equation of stationary waves. And this equation of stationary waves is applied and it can be observed especially in case of the mode of vibration of air column in organ pipes. Okay, what pipe? Organ pipe. So the topic that we now discuss in detail is the mode of vibration of air column in first we do with closed organ pipe. Which organ pipe? Closed organ pipe. Actually, organ pipes are basically two types. One is closed organ pipe, and another is open organ pipes. Okay, but before that, we try to understand what is organ pipes. Now, there are certain musical instruments like flute, whistle, clarinet. Okay, these are the musical instrument. Okay, in which sound is produced by the vibration of what column? Air column. That means any musical instrument which produce sound by the vibration of air columns are actually called as organ pipes. Okay, that's why there are certain musical instruments like flute, whistle, clarinet, even there are other musical instruments also in which the sound is produced by the vibration of what column? Air columns. And such sound producing tubes, they looks like a tube only. Okay, and such sound producing tubes are usually called as what pipe? Organ pipes. Basically called as what pipe? Organ pipe. Now this organ pipe nowadays is very famous, okay, especially for the playing with the what with the marching contingent, okay, especially in the Independence Day and all. Okay, so this organ pipe are basically two types. So organ pipes are how many types? Basically two types. One is called closed organ pipe, one is called open organ pipe. Now we discuss in detail about both closed organ pipe as well as open organ pipe. Now, but what is closed organ pipe? A tube, basically organ pipes are the tubes, okay, the tube which is closed at one end. So listen carefully, the tube which is closed at what end? One end, and open at other end is usually called as closed organ pipe. Okay, the tube which is closed at one end and open at other end are called closed organ pipe. And we learn in detail about open organ pipe also. So, but now we just focus on closed organ pipe. Okay. Now this is basically a tube having open at one end and closed at other end. And whenever the sound which is produced by these organ pipes, like closed organ pipe, is produced by the vibration what column? Air column. That's why this particular tube are basically called as what? Organ pipes. And when we hear the sound by the vibration of air columns, so remember this, children, that in this organ pipe also a stationary wave is generated. But how stationary wave is basically generated is that when we blow, okay, air from the open end of the organ pipe, a wave produces. Now, what type of wave will produces? A longitudinal sound wave produces. And this longitudinal sound wave is produces in the form of what wave? Progressive wave. Plain progressive wave. Okay, and this wave basically travel in the air of the pipe through the closed end. So blow from the open end and the wave travel, okay, from open end to the what and closed end in the form of what? Plain progressive longitudinal wave. Okay, now this wave will get reflected back towards the open end. Again it will return back to the what end? Open end. So under this case what happened? The incident and the reflected wave which travels in the air column, definitely in the what direction? Opposite direction. Opposite what? Direction. And this incident wave and reflected wave travel in the opposite direction get simply superpose each other. And when they superpose each other, they form a stationary wave. They form a what? Stationary longitudinal wave. Now why I am using the word longitudinal? Because sound can be, wave can be a transverse wave, it can be longitudinal wave. But in air, what type of wave is usually produces by the sound? Sound usually produces what type of wave in air? Longitudinal wave. While the propagation of wave is concerned, one point you need to keep in mind, okay, and this is very important, okay, that is at the close end of the pipe. So at the close end of what? Pipe, the particles of the air have no freedom to vibrate. The particles cannot vibrate at all. That means why there is no freedom for the particles to vibrate. Hence, there is always a note at the close end of the pipe. So what will form at the close end of the pipe? Always a note. Because you have learned, no, when the stationary waves are formed, the 2 points which are always formed, one is called note, another is called antinote. Note is the point where the particle have no displacement. There is no freedom to vibrate. And when there is no freedom to vibrate means there is definitely a note is formed. But where the note is formed? At the close end of the what? Pipe. Similarly, at the open end of the pipe, the particles, that means air particles, have the greater freedom, a maximum freedom to vibrate. That's why there is always an antinote which is formed at the what? Open end. So the formation of note and antinote is always happening at the open, close end and what? And open end. And in case of organ pipes, whether it's a closed organ pipe or open organ pipe, we can make the particles to vibrate in different mode. And this is different mode of vibration means the particle can vibrate with different frequency, so that we can hear a tone of different frequency and all. Okay. Now for that frequency to be measured, we now discuss in detail about the mode of vibration. Now children, we do the first mode of vibration. That means we blow the organ pipe in such a manner, so which makes the air particles to vibrate in such a way so that it will vibrate with the single frequency or the lowest frequency, and that mode is called the first mode of vibration. Okay. Now for that, let me take an organ pipe whose one end is opened. So this is a closed organ pipe whose one end is open and other end is what? Closed. Okay. So this is closed end, this is what? And open end. Now I take the case where the organ pipe has a length also, and that length I consider is what? L. So what is the length of the organ pipe? L. Okay. So length of the organ pipe is nothing but the distance between the open end and the what end? Closed end. Now I take the closed end of the organ pipe at x equals to 0, and I take the open end of the organ pipe as x equals to what? L. So the total length is L, okay, where x is 0 I take as the closed end of the organ pipe, and x equals to L I take the open end of the organ pipe. Now let me consider that these organ pipe particles of the organ pipe vibrate in such a way so that it can produce a sound of single frequency and single wavelength. Okay, and that wavelength I consider say as lambda 1. So usually lambda is the symbol we use for the wavelength. Okay, and lambda 1 I consider be the wavelength. Lambda be the what? The wavelength. Okay, I consider it is the wavelength. Okay, the wavelength of the what? Standing. Standing is also called what? Stationary wave. Wavelength of standing of stationary wave. Okay, setup. Wavelength setup in the air column. Okay, for first mode of vibration. For what? First mode of vibration. Now when a particle vibrates in air column in organ pipe, means first mode of vibration means it vibrates with a single frequency. So how can you know that this is a first mode of vibration? So in case of first mode of vibration, okay, at the close end the particle have no freedom to vibrate. So as I said already, there is a note which is formed at the close end. Note is formed at the close end, and there is a antinote formed at the open end, so that the particle have maximum displacement. So it can produce a wave inside the organ pipe, and the wave will be formed this way. So I am drawing a diagram out here. The wave will be formed this way. So the wave formed this way means the particle have no displacement to vibrate at the open end, so from only one note, and particle has maximum displacement to vibrate at the open end, which sounds antinote. So this note will be antinote at the open end, where there will be a note at the closed end. So this end is a what end? Closed end. This is the closed end of the organ pipe, and this is the open end of the what pipe? Organ pipe. This is the open end. So in case of first mode of vibration, only one note and one antinote is formed between them, between the two ends. One is called open end, another is what end? Closed end. And such mode of vibration is called first mode of vibration. But when the vibration takes place, the particle wave which propagate in the form of with a certain speed, and that speed I consider as b. So I write on that b be the what? The speed. The speed of the what? Wave. Speed of the what? Wave. And I consider that this particle of the air column in the closed organ pipe vibrating with the lowest frequency, and that lowest frequency I consider as nu1. Okay, you can write nu1 or n1 also you can use. Children, you can use any symbol. Frequency can be represented by n or nu. Because I am representing by nu, it is nu1 or n1. So this is what? This is the lowest frequency. This is the lowest frequency. This is the lowest frequency of vibration. And this frequency is also called fundamental frequency. This frequency is also called what? Fundamental frequency. So I write down this frequency. This frequency is also called what? Fundamental frequency. Fundamental frequency. Now, to express this frequency, if you look at this diagram, between open end and closed end, there are one node formed at the open end and one antinode formed at the open end, and there is node formed at the closed end. So the length of the organ pipe between the open end and closed end is what? L. And you have learned already in case of characteristics of stationary wave that distance between antinode and node. See, distance between antinode and node is always what? Lambda by 4. That means the distance between antinode and node is always equals to lambda by what? 4. And that distance is L but equals to lambda by 4. So as you know that since distance between this and antinode and node, as I said, is lambda by 4, so that length is what? L equals to lambda. But what wavelength I consider? Lambda 1 by 4. So this is nothing but the distance between what? This is nothing but the distance between node and what? Antinode. So distance between node and antinode is always lambda 1, the wavelength of the wave, by 4. So if L equals to lambda 1, distance, this node and antinode distance is also equals to L, and that L is also equals to lambda 1 by 4. So if you cross multiply, so lambda 1 equals to what? 4L. Lambda 1 equals to 4L. So if this is the wavelength of the force mode of vibration, then we can write the frequency. And you know, therefore frequency means nu1, and you know frequency is always speed by wavelength. So children, remember this, frequency means speed by wavelength, and wavelength is wavelength for the force mode of vibration lambda 1. The frequency I consider as nu1. So frequency nu1 equals to speed by wavelength. So let me just substitute the value now. B by L1, lambda 1 is how much? 4L. So frequency nu1 equals to B by what? 4L. So let me just give this in bracket. Now this is the lowest frequency, and as I said, this frequency is also called fundamental frequency. This is also called what? Fundamental frequency. And this particular tone which you can hear in the mode of vibration of closed organ pipe is called first harmonic. This is also called what? Harmonic? First harmonic. So the first harmonic is obtained on the first mode of vibration with a frequency, and that frequency is nu1 equals to B by 4L. And under this case, as I said, only the sound note produced in the pipe is also called fundamental tone. It's also called fundamental tone, or also called first harmonic of the pipe. And it is usually produced when air is blown lightly at the open end of the pipe. So how we get the first harmonic? When you blow the air lightly, very lightly at the open end of the what? Pipe. Now we go to the next mode of vibration, that is called second mode of vibration. Now in second mode of vibration, we take the same organ pipe with whose one end is closed. This is closed end. This is what end? Closed end. And this end is open end. This end is what? Open end. Okay, the length of the organ pipe is same. That length is how much? L only. The length of the organ pipe is same. That is called L. Okay, but in this case, we make the air particles of the pipe to vibrate in such a way so that it will produce a sound of single frequency, double frequency, then the fundamental frequency. And double frequency, then the fundamental frequency can occur, okay, in such a way so that it can vibrate. Okay, the frequency of vibration will be double than the single frequency. And this is actually observed by this wave. So I have drawn the diagram out here. So if you look at this diagram, the sound produced in the air column, okay, by the vibration air column in the closed organ pipe is produced by the sound of frequency which is double the what? First frequency. I means the next mode of vibration. That is the vibration of next frequency. Okay. So but remember this is a closed end where the particle always vibrate with the minimum displacement. That means the note is always formed at the what end? Closed end, and there should be the anti-note which always formed at the what? Open end. So it can be produced, okay, in such a way so that if you look at this diagram, the note is producing at the closed end, anti-note is producing at the open end where the particle has maximum displacement vibration. But between them there is note, there is note out here also, and there is what? Anti-note. So note, anti-note, note and anti-note. So this is the note of closed end, this is the anti-note of open end, but in between this there is one note also formed, okay, at this end, and there is anti-note which also formed at the other end. Because anti-note means particle have a maximum displacement vibration, note means the particle have no displacement of vibration. So this is the diagram that we exactly follow for the second mode of vibration to be calculated. Now under this case also the wavelength of the standing wave will not be same as the first mode of vibration, and that wavelength I consider as lambda 2. So lambda 2 be the what? Wavelength. The wavelength of the what? The wavelength of the standing wave. Now even in this mode of vibration, sound travel with the same speed. Okay, the speed will be what? Same. So I don't let B be the speed of the sound. The speed of the sound. Because why the speed of sound is same? Because air column is same air column, okay, and same medium means the speed will be same. But only thing is that what will change? The frequency and the wavelength are changing. So I write that frequency as nu2. So nu2 be the frequency. So this frequency can also be measured when we measure the what? Wavelength. But in order to measure this frequency, okay, so if you look at the diagram, okay, this length, okay, this particular length, that is L, the length of the air column, okay, L is equals to the mode of vibration which takes place. But look at it, how many note and antinote are formed? 2 note and 2 antinotes are formed. So this note and antinote, and you know distance between note and antinote is equals to what? Lambda by 4. So I write down lambda 2 by 4. Because the wavelength in this mode of vibration I have considered lambda 2. So distance between note and antinote is lambda 2 by 4. Plus again this note, antinote and note distance is also what? Lambda 2 by 4. Plus again this note and antinote distance is what? Lambda 2 by 4. So I have added the distance between note and antinote, note and antinote, and note and antinote. That distance equals to L. So now we take the LCM out here. So LCM is how much? 4. And this will simply 3 lambda 2 by 4. Because lambda 2, lambda 2, lambda 2, if we add, after taking the LCM, it will be 3 lambda 2 by 4. Which means if you cross multiply, we write down lambda 2 equals to 4L by what? 3. Okay, 4L by what? 3. So the wavelength of the wave produced in second mode of vibration, that is lambda 2 equals to 4L by what? 3. So if this is the wavelength, then I write down the frequency. So we calculate the what? Frequency also, and that frequency is nu2, and frequency is always what? Speed by wavelength, and that is lambda 2. So speed by wavelength is how much? 4L by 3. This will be reciprocal, so it will be 3B by what? 4L. 3B by what? 4L. So now see children, the frequency of second mode of vibration is 3B by 4L. So this is the frequency of second mode of vibration. And this frequency is actually the third harmonic. This is the third harmonic of the first tone of first harmonic. Now how? Because you know B by 4L. See, B by 4L is already what? Nu1. So I write down nu2 is 3 nu1. See, 3 nu2 is 3 nu1. Thus, the frequency of vibration in the second mode that you can see nu2 is 3 times the fundamental frequency, and that fundamental frequency is what? nu1. Okay, so the sound note produced in the pipe is called first overtone, or also called third harmonic. First overtone is also called third harmonic. Similarly, we can observe the next mode of vibration. Okay, the higher mode of vibration of this organ pipe, closed organ pipe, because as for the sequence, you can see from first mode of vibration to second mode of vibration, the frequency of second mode of vibration is 3 times the frequency of first mode of vibration. That is called fundamental frequency. That means we are getting what? Odd frequencies, odd vibration. Okay, and this vibration frequency is also called third harmonic, also called first overtone. Now we can even check for next higher mode of vibration. So next higher mode of vibration means the third mode of vibration. Third mode of what? Vibration. So in third mode of vibration also we make the air particles of the organ pipe to vibrate, so that it vibrates with the frequency, okay, higher than this second mode. Now in the last mode I'll discuss, this is the third mode of vibration. In fact, this more than this third mode can also be observed. Keep on observing. The higher mode of vibration can observe, but we do with the last mode of vibration, okay, and make the conclusion. And the third, that is the third mode of vibration. In order to make the organ pipe to vibrate with third mode of vibration, okay, now we take the same length of the organ pipe. So length is L, where the open and close end, this is a close end, the close end is x equals to 0, where x open end is x equals to L. That means the total length is what? L. Okay, but you know, in case of organ pipe, the close end always have a particle always vibrate at the close end at note, and antinote is always formed at the open end. But this is such a mode of vibration which takes place in the organ pipe, closed organ pipe. Okay, so that will make the vibration air particle vibrate to have a frequency higher than the second mode of vibration. So this can be achieved by again blowing harder to the organ pipe. Okay, so that you can see how many note and antinote are formed. Like 1, 2, 3 antinote and 3 notes are formed. See, in case of third mode of vibration, 3 antinote, 1, 2, 3 antinote and 3 notes are formed. So when 3 antinote and 3 notes are formed, then see, in case of antinote, the particle vibrate with maximum amplitude, maximum displacement, where the antinote note always has what? No displacement of particle. That means note is always formed at the close end and antinote is always formed at the open end. So that this mode of vibration is third mode of vibration. 1, 2, third mode of vibration. Okay. So in third mode of vibration, the particle vibrate with the wavelength, and the wavelength of the standing wave in third mode of vibration is lambda 3. What is the wavelength? Lambda 3. So if this is the wavelength, then I write down again in the similar manner, this wavelength length, this length L, can be even written as A by distance between antinote and note. We can do this way also, or we can even do this way also, children, just to make you understand. Distance between antinote and antinote is lambda by 2. See, distance between antinote and antinote is lambda by 2. So it will be lambda 3 by 2. Distance between antinote and antinote distance is lambda 3 by 2, plus again distance between antinote and antinote, this distance antinote and antinote is also lambda 3 by 2, and plus lastly distance between antinote and note will be how much? Lambda 3 by what? 4. So this is the way that we need to add. That means this length will be equals to lambda 3 by 2, this antinote distance, again lambda 3 by 2, that is antinote distance, and lastly antinote and note distance is lambda 3 by 4. Now if you take LCM of 2, 2 and 4, the LCM is 4, 2 divided to 4 is 2, 2 into lambda 3 is 2 lambda 3, plus 2 divided to 4 is 2, 2 is a remainder, 2 into lambda 3 is 2 lambda 3, plus 4 divided by 4 is 1, 1 into lambda 3 is lambda 3. So L equals to 2 lambda 3 plus 2 lambda 3 plus lambda 3 by 4. So if you add this, it will be 5 lambda 3 by 4. Which means, as I said, L equals to 5 lambda 3 by 4. So from here I'll make lambda 3 as the subject. So lambda 3 will be 4L by what? 5. If this is the wavelength, then we can calculate the frequency. So I write down therefore the frequency corresponding to third mode of vibration, corresponding, okay, to which mode? third mode of vibration. We are dealing with third mode of vibration. Third mode of vibration. And that frequency is marked by letter nu3. And this frequency equals to speed of the sound wave, that is b only, and wavelength is lambda 3. So speed is same in any mode of vibration because the medium is not changing. So nu 3 equals to b by lambda 3. So let's substitute the value. B by lambda 3 is how much? 4L by 5. So if I do reciprocal, it will be 5B by 4L. And this is nu 3. So look at the expression, children. The frequency of third mode of vibration, nu 3, is 5B by 4L. But you know, this B by 4L is nothing but what? Nu 1. So I write down nu 3 equals to 5 nu 1. 5 what? Nu 1. Thus, the frequency of this third mode of vibration, you can see, that is nu 3, is 5 times the fundamental frequency, which means the sound note produced in this closed organ pipe is called which tone? Second overtone, or also called fifth harmonic. In terms of harmonic, this is fifth harmonic, and in case of overtone, it is what? Second overtone. So children, we can now make a conclusion after observing this closed organ pipe vibration, mode of vibration of closed organ pipe. And the conclusion that we can simply draw is the frequencies of the fundamental tone, that is called first harmonic, okay, of fundamental tone, okay, and the overtones of closed organ pipes are basically in the ratio nu 1 is to nu 2 is to nu 3. It will keep on going this way, equals to 1 is to 3 is to 5 is to go on. That means in closed organ pipe, the higher frequency, the higher mode of vibration which takes place in odd multiple of fundamental what? Frequency. Odd multiple means like 1, 3, 5. Now next mode will be like 7 and on. Okay, that means closed organ pipe always produce a sound of frequency at odd harmonic. What harmonic? Odd harmonic. So this is the detailed explanation of the mode of vibration of air column in closed organ pipe. Now we need to do in a similar manner the mode of vibration of air column in open organ pipe. And this is the last topic that you learn, but we do in the next class. And with this, with this topic, your chapter, superposition of wave number 2 will get completed. And we do the last chapter, okay, as per the syllabus we do it, okay, and we do that much, and for class 11 syllabus. Thank you so much.